All right, we are in Unit 2. We are in Chapter 10, and we're just going over some practice problems here with the re-expressing of our data. And that was looking at the maybe possibly logging something, square rooting something, whether it's the x or the y values of your data in order to possibly make it a little more linear or straighter. Again, if I'm moving too fast through this, please make sure that you pause the videos as well, and then write them down. So here's where we left off. It says, let's try to re-express the variable fuel consumption to examine the fuel efficiency of the 11 cars. And here's the revised regression analysis. So these are the residuals now. Maybe there's kind of a pattern. Like maybe you could argue that that's happening, but I don't see as much of a pattern as before. So it explain why this model appears to be better than the linear model that we had before, right? So explain why that's the case. Here is our data to see what's happening with it, and then there's a r squared. It says using the regression analysis above, write an equation for the model. All right. And then based on the model, how many miles per gallon would you expect a 3,500 pound car to get? So let's take a look here and see what we get. So explain why this model appears to be better. Well, the residual plot for this relationship, it does appear to be more scattered. There might be a little bit of a pattern like we saw here, a little bit of one, but for the most part, there's nothing too consistent that I can tell that there's a pattern. And then part B says the linear model that we would use would be this times the weight plus that, which is what we have. And it says that's in miles per gallon if the gallons were 100, right? Because it says the linear model that predicts the number of gallons per 100 miles is gas mileage from the weight of a car. So this is basically what we're looking at. So that's how we're getting that data. So that's the linear model. And then part C, it says interpret the slope. And the slope basically is just saying, you know what, as the weight for each additional 1,000 pounds, the model predicts that the car will require 1.178 gallons to drive 100 miles. Okay, because we were basically finding it per 100 miles, giving us this as our equation that we found before. It says, based on this model, how many miles per gallon would you expect a 3,500 pound car to give? So that's where the weight goes. But remember, it's in thousands, so that's why they moved it over to 0.35. So this is what we would expect to get in the car. Right? So we plug it in to end up getting that. And it says, according to our model, a car that would weigh 3,500 pounds, right, is expected to require approximately 4.478 gallons to drive 100 miles. That's how many gallons that you need to drive 100 miles. Or roughly, it is that per mile if we use it, which is approximately, if you divide it, 21.06 miles per gallon is what you would end up getting. But this would have been fine. You didn't have to switch it either way. So it gave us a better linear model to calculate what's going on, basically. Taking a look at this scatter plot shows the gross domestic product of the United States in billions of dollars, and it's plotted since 1950. Okay, so this is years since 1950. And as you can see, some would argue, oh, it looks pretty straight, and it could be, but it also looks like it could possibly be curving a little bit, just a little. And it says your linear model fit to the relationship looks like this, if I was to do a linear model for it. And it looks R squared, I mean, like, looks pretty good. Like, to have 97.2% of the gross domestic product variability be associated with a variability of years since 1950, right, of the billions of dollars. It's not that bad, right? But does this suggest that it's a good model? It suggests it currently, but we need to do a little bit more, right? So the re-expression is not useful, right, because the student has gone too far down the ladder of powers. We now see marked downward curvature and increased scatter plot. So what this is basically implying is the question right here says, does the value suggest that this is a good model? And most kids tend to look at this and say that that must be. But the real way that we're going to find this out is you have to look to see if there's a pattern at all with the residuals. All right, that's the best way to do it. It says this re-expression of data, it's not going to be useful because it says here again that the student has gone too far down the ladder of powers. All right, meaning when we're looking down there trying to figure out the ladder of powers that we went over, like are we doing logs of both? Are we doing a log of one? Are we doing square roots? Are we doing reciprocals? All right, we now see marked downward curves and increasing scatter plot, basically, is what we're getting at, right? So take a look here. Just so you understand here. Here's a scatter plot of the residuals, right? And the point is, if you look at a scatter plot of the residuals, you can see why. Oh, right away. That's probably why it's not the best fit, because I'm noticing a pattern, right? So how do you think this is a good, now do you think it's a good model for it, right? Is what they're basically asking. And it says the next step would be to try a weaker re-expression, like maybe you try the reciprocal square root or a log, right? Seeing what you can do to figure it out. So maybe you try one of those to re-express the data, is basically what they're saying. So having gone too far, the student should move back up the ladder. Because again here, it says when they were doing this problem, all right, it says a linear model fit to this relationship. They're looking at it, and we don't know how they re-expressed it. All right, maybe they just divided. We don't know what they did because it wasn't given, but that's the point. All right, what they did to re-express this made it more concise than curves. So you can't just assume because you re-express the data, it's good, because as you can see here, I'm noticing from there that it's curved. It says whatever we did to re-express it, that didn't help, because my residual plot, I'm noticing a pattern, and that's not good enough. So they're saying try a different way to re-express it. So consider again, right, we examined exercise 11, all right, here are a regression and residual plot when we use the log. So now they're saying, you know what, if I did log of it, look, that's 99.4. And when I logged it, and I looked at the residuals, it's kind of looking like maybe it fanned out. Is it better? Personally, I think it's better, but is it the one I want to use? That I don't know, right? It says it's a better model, although there is still some pattern in the residual because it looks like it's fanning. It's better than the pattern that we saw before. So the pattern isn't as strong. So meaning not only is this higher, but us logging, it says here the residual, we logged the GDP. All right, we logged the GDP. And then after we log the GDP, this is what happens. So this looks better, is the point. The table below shows stopping distance in feet for a car tested 3 times at each of the 5 speeds. We hope to create a model that predicts stopping distance from the speed of a car. So we have 20 miles. If they're going 20 miles per hour, the stopping distance is 30 miles per hour. Their distance is 40, and so on, right? It says explain why a linear model is not appropriate. Re-express the data to straighten the scatter plot. Create an appropriate model, then estimate. So basically they want you to do a scatter plot, then realize why it's not good, and then recreate another one, and then plug in some stuff to estimate it. So, point is, explain why a linear model is probably not appropriate. Well, the association between speed and stopping distance, all right, is strong, positive, appears straight. And how could you do that? Well, you could plug this in on the calculator, right? Plug in your points. Let's see what you get. 20 stopping distance, 20 stopping distance, 20 stopping distance, and 30. Like, you could fill this in to see what you would get. But it says higher speeds are generally associated with greater stopping distance. And look at it. That's seeing to happen. The point I'm getting at is that how could I see this without it? It does appear to be going up. At speeds of 20, 30, right, they keep going up. So it does look like, regardless of where you plotted the points, that they do appear to be going up. It does appear to be positive. It would appear to be kind of straight, like they aren't like out of the ordinary. So it says higher speeds are generally associated with greater stopping distance. And the linear regression model with the equation, if you were to plug all of these points in to figure it out, this is what you would end up getting. So I'm saving you the time, but if you were to plug them all in, using your data to figure out what you would get, this is basically what you would get. And then it's saying that you have an R squared of that, meaning that the model explains 96.9% of the variability in stopping distance, right? So that's your X and that's your Y. It explains that much of it. However, the residual plot has a curved pattern. So if we're doing this and it has a curved pattern, the linear model would not be appropriate that we have. So a model using re-expressed variables would be better used. So, taking a look here, if you looked at the points, right, the speed and the stopping distance, there it is, just so you can see what the graph looks like. And then there's the residuals, right? So I'm just trying to show it to you. You could have done all this with your calculator, but as you can see, if you were to plot them with your calculator, that's what it looks like. And then the residuals, it, looks like there's a pattern here for the most part. Like it does look like it's kind of curving up. So that's what they were getting at. So we re-express the data to straighten the scatter plot. Stopping distance appears to be relatively higher for higher speeds. Basically what they're saying is as the x goes up, so does the y. It seems that way. This increase in the rate of change might be able to be straightened by taking the square root of the responses. So oftentimes, here's a tip for some of you. Oftentimes, if you're noticing that the larger the x, the larger the y normally, then you might want to try to square root it to see what happens. So square root of speed versus, you take the speed, but you square root the y to see if that lowers everything down and makes it straighter. Seems like it might straighten it out. So if we do that, all right, square root of the distance, that's what I get. And now if I look at the residuals, for the most part, I don't know if there is necessarily a pattern like that I could argue, so that might help it out a little bit more. So now we did that, create an appropriate model. So here's our model, right? It's a square root of the distance, like it's literally what you just did to it. And if you were to square root the distances and then try it again, that would be your r squared. So now you would say that 98% of the variability of the square root of the stopping distances can be explained by this, by the speeds, basically. So now estimate the stopping distance for a car traveling 55. So now we plug in 55, but in order to get the final answer, we would have to square it, giving us about 263.4. That would be roughly the stopping distance, right? And then according to our model, a car traveling 55 miles per hour is expected to require approximately 263.4 feet to come to a stop. And then estimate the stopping distance for a car traveling 70 miles per hour. Plug in 70, right? Then you square it. So according to the model, a car traveling 70 miles per hour is expected to require approximately 390.2 feet to come to a stop. Then it says, how much confidence do you place in this prediction? It says the level of confidence should be quite high because this right here was high, right? 98-ish%. And the residual plot was reasonably scattered. So the prediction for 70 miles per hour is a bit of an extrapolation because it's outside of it, not by much. It's outside of it, but should still be a reasonable conclusion that we can get. When I come back here, we'll take a look at the planet distances and some more practice problems.